Hello everyone, welcome back to United Engineering. Today we are studying strength of materials and structures N5, and the opening topic will be stress and strain. We already know about stress and strain. We did stress and strain in engineering science N4. So today we are just going to recap on some of the terms that we have already looked at or on our engineering science N4. So we're going to start with stress. Stress, we know stress is given by force divided by area. And stress is defined as the force that is applied on a cross-sectional area of an object. Meaning, if we're having an object like this, and we calculate for the area of this object, let's say we get that the area is equals to 4 square meter. This tells us that the object can be divided into 4 sections, each section being a square meter, And then we are going to take the force that is applied. Let's say the force is 20. If the force is 20, we're going to take the force that is applied and divide it into 4. Divide it by 4, rather. Divide it by 4, or divide it into 4 equal parts, which will be applied on each and every square meter of the object. In this case, we are going to get 5 newtons, meaning 5 newton will be applied on this section, 5 newtons, this section, and this section. The 5 newton will be applied on each and every square meter of the object, depending on the number of square meters that we have. Therefore, we're going to say that 5 newton will be applied on each and every square meter, which will be 5 newton per square meter of the object. Or we can just say it's 5 Pascal. Pascal is the SI unit of stress, and it is derived from here. If you get an SI unit, they say Newton per square meter, it's the same as saying Pascal. So from there, we go to strain. Strain, when we talk about strain, we are talking about the change in length per unit length of an object. So let's say we are having a 1 meter object. 1 meter. The change in length of this object can be classified as strain. Will be classified as strain. It can be the change in length of the object, and it can also be the strain of this object. Why? Because the length of this object is 1 meter. So if we are having a 20, let's say from here to here, let's just say 5 meter object. From here, the change in length, it's not equal to the strain. But we can get the strain using the change in length by using the formula to calculate strain, which is change in length divided by the length. Here we are looking for the change in length per unit length. Here we are having the total change in length caused by the 5 meter length. We want the change in length now caused by a 1 meter length. That is why we are going to use this formula, and that length we are going to call it the strain. The strain is the change in length per unit length, and it's calculated by change in length divided by length. And we know this is meters. This is meters. This and this will cancel. Even if this is millimeters, we must also use millimeters. The SI unit should correspond. This and this will also cancel. Therefore, the strain is unitless, doesn't have any units. And then we go to the types of stresses. We are going to deal with 2 types of stresses here. We do not have 2, there are more than 2. So here we're going to deal with the direct and the shear stress. The direct stress, it's caused by a force that it's applied directly on the cross-sectional area that it's affected, or the cross-sectional area that we are dealing with. The force will act perpendicular to the cross-sectional area that we are dealing with. And the shear stress, on the other hand, let's just make the same. Okay, let's start here. The direct stress will cause the object either to compress, or it will try to change, to increase, or to elongate the object that we are working with. And then, let's erase this. The shear stress, let's use the same cross-sectional area. The shear stress, when it comes to the force that causes a shear stress will not be perpendicular to the cross-sectional area that we are working with, but it will be parallel to the cross-sectional area that we are working with. So let's apply the same force here on this cross-sectional area. If we were to deal with this cross-sectional area, we are going to say this is a direct stress caused by a direct force. But let's say now this plate or this object is fixed in the ground so that it is not moving. But the force that is applied, it's great in such a way that it causes the object to separate here, and this portion to move in that direction. This portion will come here. We can tell now that the cross-sectional area that we are dealing with is no longer this one, but it's the cross-sectional area where the two objects, because now we are going to have two objects, where the two objects separated, which will be this cross-sectional area. And we can see that this cross-sectional area is parallel to the force that it's applied, since this is the cross-sectional area and the force is also applied in that direction. They are parallel to each other. Therefore, that we are going to say is the shear stress. The shear stress, the characteristics of the shear stress is we are going to see an object shearing at some position, meaning they are going to separate. And that area where they separated, that is the area that we are dealing with. That area should be parallel to the force that is applied for us to be able to consider that as a shear stress. I know shear stress can be confusing sometimes, but we are going to deal with it in a more detailed way when we are doing exercises. But the main thing that you have to understand and know is that shear stress is caused by a force that is parallel to the cross-sectional area that we are dealing with. And then direct stress is caused by a force that is applied directly on the cross-sectional area of the object. Or we can say the force is perpendicular to the cross-sectional area that we are dealing with. You know, perpendicular is this one. There's a 90 degrees here. So in direct stress, we have two types. We have the compressive and we have the tensile. A tensile stress is caused by a tensile force. This we are going to call tensile force. And the compressive stress is caused by a compressive force. This we are going to say it's a compressive force. So they are both given by the formula, which is force divided by area. But now, for stress, we're going to represent it as tau. Yeah, this symbol. For direct stress, raise this. We are going to represent it by this formula, this symbol. And the formula is still the same. SI unit is also Pascal. And here it's also Pascal. So looking at this diagram represents a beam. It's one beam. But the thing about this beam is it has different cross-sectional areas, meaning it has sections. So it's possible that you can get a beam that has different cross-sectional areas, saying this is a beam, and then all of a sudden we are going to have, it's not necessarily a beam, but the member that we're working with, all of a sudden we are now having a circular part. So the cross-sectional areas that we're dealing with is this, it's one, this is one, and then is this one, this is two. This, remember, it's one thing. So if you are given something like this, you have to treat them separately, because you can tell that the cross-sectional of this and this are not the same. So you can't treat them as one thing, although they are one thing. So what we are going to do is we are going to divide this beam into sections. In this case, it will be this one, section 1, and this one, section 2. So here we are having 3 sections. What we are going to do is we are going to divide them into 3 sections as if you were dealing with this one. We are going to calculate for the area, the change in length, the stress, and the strain of this one section separately. Calculate for the area, change in length, stress, and strain for this part separately, and also this part separately. And if you're wondering what X is, X it's the same as change in length. Most of the books they use in this topic, strength of material, we mostly use X as the change in length. So even if you write change in length as delta L, it's the same thing as writing it as just saying X. So yeah, if you were asked to calculate for the total length will be the length of number 1 plus the length of number 2 plus the length of number 3. If you were to ask for the total change in length, which will be X, total X, it will be change in length number 1 plus change in length number 2 plus change in length number 3. And if you were to ask for the total strain, same thing apply. Strain 1, strain 2 plus strain 3. This is 3. So if you are given a member with different cross-sectional areas, you have to treat them separately, and then at the end, if you ask for the total length, total change in length, total strain, that's what you are going to do. We do not have the total area and the total stress. I've never seen these two being asked, but yeah, total area and total stress, I'm not going to ask for that. And then we go to what we call modulus of elasticity, also known as Young's modulus. Also known as Young's modulus. It's represented by a capital letter E, and it's given by the formula stress divided by strain. So we remember that stress is given, the SI unit for stress, it's Pascal, and strain doesn't have any unit, it's unitless. Therefore, the Young modulus of elasticity, also has an SI unit of Pascal. And then now, the Young modulus of elasticity will depend on the material that we are using for the member or beam that we are dealing with. So let's take an example. We are having 2 beams of the same cross-sectional area. This is beam number 1. Then this will be our beam number 2. Let's say they have the same cross-sectional area, same area here. And there is a force that is applied. The force, it's the same as well. We have the same force, we have the same area, meaning stress number 1 will be equals to stress number 2, since we know that stress is given by force divided by area. And then we come and say the only difference that we have between these two is that this beam, which is beam number 1, is made from steel, and beam number 2 is made from copper. Young's modulus is given by stress divided by strain. The stress is the same, but the strain will depend on the material used for the beam. We know that steel will stretch less compared to copper. So the material that is made from copper will stretch, will have a greater or a larger change in length compared to the steel. So now let's say we're having a stress of 100 for both, since they have the same stress of 100. But we know that steel is going to stretch, it's not going to stretch that much compared to the steel, to the copper. So let's say the change in length or the strain of the steel is 0.1 and the change in length for the copper is 0.5. If we calculate this will give us a strain of 1000, which will be Pascal, and this will give us a strain of 200, which will be Pascal as well. So from here we can see that the material, the stronger the Young's modulus, the larger the Young's modulus rather, the stronger the material. The smaller the Young's modulus of elasticity, the you can say weaker. But yeah, if we were to compare two objects and we are given the Young's modulus of each and every object, we can say that the object that has the small amount of Young's modulus, a smaller number for Young's modulus, will be less strong compared to the other object. And we can derive the formula for Young's modulus, since we know that it is stress divided by strain. It can also be stress divided by Lx, or it can be strain divided by F L, this is F Ax. This, we know strain is equals to divided by this, by the original length. So we're going to put it here. It will be, if we were to substitute this by this, and then we know this will go up. That's why we're going to end up with this formula. So you can either use this formula, and this formula, depending on the information that you are given. And that will be it for this video. I will see you on the next one.